Dr. Guruvidyarthi sir, Assistant Professor from Hyderabad Central University. I welcome you, sir. He will be giving talk on high entropy alloys. A small introduction about Guruvidyarthi sir. Dr. Guruvidyarthi is an assistant professor in the School of Engineering, Sciences and Technology, University of Hyderabad since 2020. He did his BE in Metallurgical Engineering from Anna University, his master's from IIT Madras. He has 4 years of industrial experience in steel, automotive and power sectors before PhD. He got dual PhD degrees, one from IIT Madras and one from NTHU Taiwan. His research interests are computational materials engineering, especially computational thermodynamics, Calford, thermodynamic assessment, alloy design, and non-equilibrium microstructure predictions. Till date, he has about 15 research publications and a book chapter. He also conducted hands-on workshop on thermocal software to various organizations. He teaches material modeling, thermodynamics, and phase transformation. He also frequently publishes videos which are animation enabled for effective learning of other subjects, which is open to all through his YouTube channel, Thermomatter. The materials of his interests are high entropy alloys, nickel-based superalloys, and shape memory alloys. Today, he will be presenting on high entropy alloys. Welcome you, sir.
Thank you, Dr. Padmanabha. Thank you for inviting me. I'm happy to be here. Let me start sharing my screen. Is the presentation visible now? Is it visible? My screen is visible?
Yes, sir, we can see.
Yeah. Yeah, okay. Fine. Okay, so this talk is going to be on high entropy alloys. So this is one new class of materials which are being explored from, I would say, 2004. Although in 1980, some work has started, 1996, something more concrete was started. In 2004, first publication started coming out. So from then on, high entropy alloys are quite hot. For example, you see this graph. This is downloaded from Scopus. In 2004, you can see the number of publications which has this word high entropy alloy in either title or abstract or keywords. So the documents are very few, less than 10 in 2004. And then about a decade later, if you see, the number of publications go up. And for example, in 2020 alone, there were more than 1,500 publications. Okay, so you can see the kind of excitement in the field. Okay, what is so great about this high entropy alloy? And since this is being a field of a new alloy development, everything that is there in new alloy development, right from extraction to making a product and to see the environmental damage and things. So there are a lot of things that one can talk about when we want to talk about high entropy alloys. The one which I chose to talk today is something that is not too much of various aspects of various aspects of this material development. I would like to focus on something very small and concrete, so that as mechanical engineers, I assume most of you are mechanical engineers. So as mechanical engineers, this 1.5 hours will be useful for you, so that from where you are, you can add something to your knowledge base. Okay, so that is the idea. So the orientation of this particular 1.5 hours lecture is going to be on this kind of flavor. How you would have discovered high entropy alloys. Okay, so this is the theme in which I want.
Sorry for interruption, sir.
Yeah.
Can you just increase the volume, sir?
Volume, I think. Is it okay now?
Yes, sir. Now it is very clear.
Yeah, okay. So this is going to be the talk's theme today. How you would have discovered high entropy alloys on your own. So in this direction we will travel. We'll see some kind of a hypothesis generation based on various knowledge that we have in materials, and then see whether that hypothesis worked out or not. and what was the way forward. That was done in the last 1.5 decades or so. Okay, so that is our theme today. So this is Brian Cantor is I would say one of the first persons to start this high entropy alloys. He didn't coin the term high entropy alloys. What he said is this: we are very fortunate as material scientists. The world of materials is literally enormous. There are trillions of stars in the universe, but there are millions and billions more new materials that haven't been investigated, just like new stars. That's quite a strong thought. So this is what he told about new materials. So there are numerous materials the words are millions and billions used by him, which is literally true if you work out the number. So the excitement will start from the sheer number of alloys that are waiting to be explored. So that is where I also would like to start. This is Professor JWA. He is the one who is credited most for discovering this group of alloys. So he is from Taiwan. Incidentally, he happens to be one of my PhD supervisors. So he is presently above 70, I guess, still working on high entropy alloys. So this is an interesting point to start. What is this 85.555%? This is something like a conventional alloy. For example, you know about steels, aluminum alloys, copper alloys, and so on. Okay, for a high alloyed steel, let's say 80% would be iron, and in the remaining 20% there can be other alloying additions, elements like nickel, chromium, and so on. Okay, so I am assuming 5% of 4 different elements, 4 different colors, and 80% is iron. Okay, in this case, if I change this 5%, let's say the element in red color, okay, I make it to 4%, and whatever that 1% loss in that element is compensated by iron or some other colored element. Okay, in that way, 1% of one element, if I start changing, how many number of alloys can I have? So if I work out the combinatorics, it comes to be something around 4,800. Okay, which is already enormous, 5,000 almost. Okay, even when I have one element as 80% and change only the rest of 20% with 4 elements. Okay, so that is enormous. But what about this kind of alloy design? 5 different elements, each of them 20% each, and I can change them from 5% to 35% each element. Accordingly, I can adjust some other element among these 5. So I will increase one element by 1%. So the grid size I'm choosing here is 1%, which is already very high. If I choose 0.1 or 0.01, it will still result in a new alloy. You know, stainless steel, if for example, SS304 is one stainless steel. It has 0.08% carbon. Okay. And there is another grade called 304L stainless steel, which is 0.03% carbon. So 0.08 carbon to 0.03% carbon results in 2 different grades of stainless steel. So I am here not talking about 0.0 some number kind of variation. I'm talking about even 1% variation. In that case itself, I get a number like this, 1150626, enormous. So now already we are entering into the range of millions. Okay, so if you start reducing the grid size, so changing the elements percentage very little, then you will see the numbers that Brian Cantor has mentioned, millions and billions. Okay, so that is the number of alloys which are not yet explored. Okay, so if you see any standard alloy like a steel, there are almost 2,000 type of steels which are in use today. Okay, 2,000 type of steels, 2,000. We are still in thousands. Okay, and these high entropy alloys are like this: 5 to 35% of one element and 5 elements in almost equal amounts. So this is the kind of alloys which are called as high entropy alloys. Okay, so in this, the possibility is so high that should we really call it as a new class of alloys which are something like conventional metals and alloys? As conventional metals are still in the range of thousands. Now there are some things which are which is a very big set. Okay, we can even say conventional alloys are possibly a subset of this kind of alloys. But only thing that stops us from saying that is, in conventional alloys we have one element dominant. But in this, the idea itself is putting more elements in almost equal amounts. So that is the way in which high entropy alloys differ from conventional alloys. Okay. So there are so many number of elements which are added in this equiatomic kind of ratio, which results in high entropy alloys. And the number is so high that there is a lot of excitement which is there in the field. So people are exploring left and right all these possible alloys. Okay. So anything related to materials, any subject related to materials should be mapped into this particular materials tetrahedron, I would say. If at all you are coming across any lecture, any particular subject that is related to materials, see where it lies in this materials tetrahedron. So most of you would have seen this. Basically tells us that processing is related to structure, which is related to properties, which is related to performance. And of course, all these are interconnected. Okay. An easier way to visualize this is a linearized material tetrahedron, I would say. So I usually present this rather than the previous one. Okay, so we'll start from the left, processing. So there is another entirely new kind of activity, which is choosing a composition, and only then we go for processing. Since materials tetrahedron generally starts with this processing, I would put the composition selection in the first part itself. So processing starts with choosing a composition, and then you go for any manufacturing process, casting, forming, heat treatment, welding, and so on. Okay, what all these are going to result in is a certain microstructure for the material. And in microstructure, there are things like phases, grains, morphology of phases, etc. We will see about that with pictures so that you will have some more concrete pictorial imagination to assist your understanding. Okay. Then this microstructure is the one which controls the properties. So most of the mechanical engineers bother about composition, manufacturing process, and properties. The in-between thing, which is the microstructure, that is the part where metallurgists come into picture. Okay, so understanding the microstructure, how it relates to the previous step, processing step, and to the property step. Okay, you tailor the microstructure, you are able to tailor the properties. So that's the power of understanding the microstructures. Okay, so there are certain things which we will talk in detail in this. First is about choosing composition in the processing part, in the microstructure part about the phases, in properties part about the first four properties: strength, hardness, ductility, toughness. Okay, and then these properties enable the application. Okay, so contents of the talk are going to be like this. I will fit whatever I'm going to talk in this material tetrahedron. Okay, first we'll talk about composition. As I showed in the first slide itself, it's basically trying to find out which composition of high entropy alloy is good. That is the hunt for better and better high entropy alloys based on composition selection. So that is the most critical part. Okay, then phases. In the microstructure, we will talk about phases, especially two phases. One is solid solution, other one is intermetallics. Okay, and in the properties, we will talk about two properties: strength and ductility. Most of you know that these two are opposite to each other. Okay, and the strength, we are talking about yield strength as well as ultimate tensile strength. Okay, mechanical engineers, when you study this strength of materials, mostly you stick yourself with elastic limit, and you talk about moduluses more, all this bending moment, all those things, where you talk about structures where you don't really talk about stresses beyond the yield point. But the concern is when it comes to materials design, strength and ductility in terms of plasticity I'm talking. Okay, so that plasticity is opposite to the strength. If strength is high, ductility is low. So this kind of a thumb rule you might have heard. So the holy grail of most of the structural materials or mechanical behavior related materials development studies focus on this: how to increase strength without compromising ductility, or how to increase ductility without compromising strength. Okay, so we will also try to see how this hunt gave rise to high entropy alloys. Okay, and in this process, connecting the composition to microstructure, there we have to understand certain things about phase diagrams, which you might have heard in mechanical engineering BTech itself. There is one course at least for materials engineering which talks about certain phase diagrams, and the thermodynamics, which is the basis for phase diagrams. And when it comes to thermodynamics, it is the Gibbs energy which we need to understand more. So Gibbs energy is the one which gives the maximum difference between thermodynamics of mechanical engineers and thermodynamics of materials engineers. Okay, mechanical engineers bother about efficiency of engines and so on. Materials engineers bother about reactions, phase transformations, and things like that. In both the cases, same thermodynamics is used, but there the terms are a little different. Here Gibbs energy is the one which is the criteria for which phase will form, which product will be stable, and things like that. Okay, and of course the term entropy is there in the name of the alloy itself. Okay, so that is another thermodynamic quantity which is important here. In fact, from second law of thermodynamics only this entropy comes, and from this entropy only Gibbs energy is formulated. So these are related, but how to increase this entropy will be one of the targets in the presentation that I'm going to give. So keep that in mind. We'll go towards how to increase this entropy and stabilize certain structures, certain microstructures. Okay, so that will be the hypothesis generation part. After that, we will see whether that hypothesis works or not, whether the idea of high entropy alloy philosophy, whether it works or not based on whatever has been done in the last 20 years or so. Then we will see how to design certain high entropy alloys according to our wish. Okay, so this particular composition design method is where my entire research expertise lies, which also connects this composition to microstructure. Okay, so wherever I give talk, mostly I give the entire hour only on these compositional design methods based on computational thermodynamics. But here, since it is for a different kind of audience, I made it in this way, how this entire material tetrahedron comes into picture and how can we design a high entropy alloy on our own. Okay, now I will talk very briefly about my own research area, that is the compositional design methods. Okay, fine. Then we will see some promising properties that we see which can give very high performance, so that the excitement of high entropy alloys still remains, and you can see how much big promises it can make. Fine. So kind of a summary about what is happening now. Composition wise, high entropy alloys are very different from conventional alloys. In conventional alloys, there are one or two major elements. Example, steel is based on nickel, superalloys are based on either nickel or steel is based on iron, superalloys are based on either nickel or cobalt and so on. Okay, and for high entropy alloys, we cannot say there is a base element. That's the first difference. There can be multiple base elements or multi-principal elements. For example, this one, cobalt, chromium, iron, manganese, nickel. So there is no subscript for these things. That means they're all 1, 1, 1 each, 20, 20, 20, 20, 20 atomic percent. Okay, so this is one famous high entropy alloy. And here there is a subscript for cobalt, 0.5, which means all others are in 1 mole, and this is about half a mole of that. So that is the kind of alloy design that is done in this particular alloy. So this is a composition. So these are all called high entropy alloys. So not just cobalt, chromium, iron, manganese, nickel. You can think about, in principle, any 5 elements in the periodic table. The design philosophy should work. Whether it works or not is a different question, but the hypothesis generation part will not have that. Okay. So let's see. So guidelines. How can we say something is a high entropy alloy? Okay. These are guidelines, not strict definitions. One is this: 5 to 35 atomic percent, and there should be 5 or more elements. So that is high entropy alloy. It may also contain minor elements, like 1% or less kind of elements also. But at least there should be 5 elements in equal amount or in the 5 to 35 atomic percent range. So minimum is 5. That is one criteria. And then this delta S configuration. This is one thermodynamic property. We will talk about that in detail. That property value should be more than 1.5 R. This is another definition kind of for high entropy alloys. Then generally speaking, these are equiatomic or near equiatomic alloys. All are equal in amounts, basically, all elements. And these are concentrated. I said minimum is 5%. That means it's not a dilute solution kind of thing. All the elements are in quite concentrated amount. Okay. So yeah, So now in this journey of hypothesizing about high entropy alloy design, first thing that we need to understand is phases in microstructure. Okay. So microstructure itself, like you can see like this, if you have not prepared any metallography samples before, this is what we do. We take a sample alloy, put it in a kind of a mold like this, polish it, observe it under microscope. We see different things like this. Okay. So in one metal, it can be like all are single color, single shade of gray with some boundaries. So these are grains basically. And there can be two different kind of colors. Here it is black and white. These are again grains. What is the difference between these two microstructures? One is microstructure of only one phase. Other one is microstructure of two phases. Okay. So depending on the materials composition, we can have either one phase or two phase or multi phases. Also, we may have something like this. This is again two phase, only two colors you are seeing, but the morphology is different. Morphology is basically the shape. Okay, that is different here. So each one of these will give certain strength, certain ductility kind of properties. Okay, I'm talking mostly about mechanical properties. You can think about functional properties as well: magnetism, electrical conductivity, thermal conductivity, optical properties, and so on. All of them are affected by the microstructure. Okay, and in this one phase, let's say this white phase, that will have a particular crystal structure. Let's say BCC, body centered cubic, face centered cubic, and so on. The black phase will have some other crystal structure. Composition also will be different for white phase and black phase. Okay, so understanding these phases is critical, especially phases which are called as solutions and phases which are called as compounds. Let us understand this. Imagine a glass of water. It's a single phase. Okay, it's a compound H2O, clear. Let's imagine we add a spoon of sugar. So this is also a single phase. It's a compound. This is the chemical formula for that compound. Let's add that sugar. Okay, what happened? That sugar has dissolved. This is a solution. This is a single phase. Okay. Now the word phase means all the three, whether it is water, which is a single compound, that is single phase, sugar, which is a compound, which is again a single phase. Once the sugar is dissolved in the water, formed a solution, that solution is not two phase. That is also single phase. Okay. So solution can be single phase. That's the first understanding that you are taking. Let's say we add more sugar. Yeah. And if we keep on adding, what will happen? At certain stage, there you will see that sugar precipitating. It will not dissolve. What does it mean? It means that the liquid has certain saturation limit to accept the sugar. Okay. So beyond that, if you add, that sugar will be precipitating. So here what do we have is a two-phase system. A saturated solution which cannot accept any more sugar, and then a sugar. Okay, so these are two different phases. So it's a two-phase system now. So I hope you get the idea of compound and solution now, and one single phase and two phase now. Okay, so the important thing is this: the compound has a fixed composition. 12C should be there, 22H should be there, 11O should be there. There is no compromise. So composition is fixed here. That is compound. H2O also is similar. But for the solution, it is different. There can be a range of composition. From 0 to 220 grams of sugar in 100 ml water at room temperature. This entire thing is one solution only. It can be 50 gram sugar, 100 gram sugar, 220 gram sugar. It's all a single solution only. Okay. So the at room temperature is written here just to tell you that this maximum limit depends on the temperature. Okay. So this is how in the atomic scale that solution looks. In the left side, you have these big molecules, which are sugar crystals. One sugar crystal, basically these are sugar molecules arranged in a particular order because it is a solid. And this entire thing surrounding is randomly moving H2O molecules. Okay. And what happens when sugar dissolves is This entire molecule detaches from the crystal and moves into the water, and the molecule remains as the molecule. Sugar molecule does not dissociate into carbon, hydrogen, and oxygen separately. It still remains as sugar molecule, and it is suspended in the water molecules. Okay, so this is how the solution looks. Fine. Now, since you have understood how a solid can dissolve in a liquid, we can also think how a solid can dissolve in a solid. So that is called a solid solution. Okay. For example, this one we will directly see in the atomic scale. So this solvent atoms are nickel, the white atoms, and solute atoms are copper, the gray atoms. Okay. So some of the nickel atoms from their actual crystalline position, they are removed and replaced by copper. Okay, so this is what happens when copper and nickel are there in the solid state in a dissolved condition as one single solid solution. Okay, so this is copper dissolved in nickel. This is called a substitutional solid solution. One more jargon, because copper is substituting nickel. Look at this one. So here solvent atoms are iron, these white atoms, and solute atoms are these black ones, which are carbon. Okay, so they are sitting in the gaps between the iron atoms, so they don't really replace the iron atom and sit. So this is called as carbon dissolved in iron and interstitial solid solution. Okay, so it's another difference from substitutional. Okay, so here individual solute atoms sit among the solvent atoms. So this is also atomic level dissolution. In the previous case, I said the sugar molecule remains as sugar molecule inside the water solution. But here it is individual atoms of copper and nickel. Okay. So please wait for a moment. I have to connect to power. Is it visible now, my screen?
Yes, sir, we can see, sir.
Yeah. Okay. So about solid solutions, we have just seen. Yeah. So this is the range 0 to 100% of copper can dissolve in nickel, which means when you go to 100%, it is more like nickel is dissolved in copper. So the entire range of solubility is possible in nickel copper system. Okay. And in case of carbon in iron, it is up to 2%. And the important thing is this one, solutions have random mixing. So if you see this gray atom and white atom, they can interchange their positions and it will still be called as same solid solution. Okay. When it comes to compounds, we will use the word intermetallic compounds for compounds in this kind of metals and alloys. When we talked about sugar or water, we don't use this word intermetallic compound as there is no metallic element involved there. Here in metals and alloys, we'll use the word intermetallic compound. Conceptually, you can keep the idea of compound in your mind, which has fixed composition and all. Okay. For example, Fe3C. 3 iron and 1 carbon in this particular stoichiometry in this structure. Okay, so this is the structure. 3 iron, these big atoms, and 1 carbon, the small atom. This is one unit cell where you see certain iron atoms and carbon atoms in particular orientation and all. They cannot interchange their position. The big atom cannot come to the small atom's position and small atom cannot go to the big atom's position. If it happens, it will not remain as Fe3C. This crystal structure has to be maintained with this particular position for this particular atom. Okay, so this is another important thing about intermetallic compounds. So why are we learning about this solid solution being random and these compounds being very strict in their stoichiometry and crystal structure? Okay, it has to do something with the properties. We will see that in the next slide. Okay, so here there is a chemical order and the mixing is not random. Clear? Chemical order is basically carbon is one chemical element, iron is one chemical element. Since they have a particular position and cannot interchange with each other, it is called as chemical order. Okay, so we will understand something about properties, strength and ductility, and then connect it to whatever we have understood just now about solid solutions and intermetallics. Okay, so strength versus ductility. Strength is always versus ductility, and strength increases, ductility goes down. We would like to have both uh, uncompromised when we try to design a new alloy. Okay, so this one core concept from mechanical metallurgy, I would like to make you understand. This is called as the dislocation theory. Okay, the entire dislocation theory has so many things. This one I would say is the essence of most of it. Okay, so if you try to understand this slide, most of the mechanical metallurgy related to plasticity is easier. Okay, so moment of dislocation is what makes a material ductile. When you give a stress and materials change their shape permanently, plastic deformation, what happens inside is something called as slip. It's called dislocation slip, which is nothing but movement of something called as dislocation. Okay, if that happens, only then material deforms. Okay, so we'll see what is that. You look at these white atoms here. This is one material's crystal structure. I mean, inside one grain, you are looking at what is happening in the material, atomistic level. Okay, so these are the atoms of one crystal, and these red atoms are also same crystalline materials. The reason why they are in red color is this bottommost atom do not have another atom to bond here. If you see this, I will just click my laser pointer. So if you see this white atom here, this has some atom to bond here below, but this atom doesn't. Okay, so what this means is that this plane itself is like a defect. So you are if this red atom's plane is not there, then everything will be smooth and good looking, right? So without any defect, that is a perfect crystal. So now we have these three atoms coming into picture, and that is marked as extra plane of atoms in crystal. So we are seeing only one line. What is this plane we are talking about? The plane is nothing but behind each of this atom, you have to consider a line of atoms. Okay, opposite, perpendicular to the screen, you have to imagine one line of atoms behind all these atoms. Okay, so that is like these three atomic lines, which is put together called as a plane. Okay, so that is an extra plane. What is important here is the bottommost atom. Entire line of atom behind this bottommost atom do not have a neighbor to bond below. Okay, so they are in a quite excited state. Okay, the reason why atoms bond to neighbors is to become more stable, reducing their energies, Gibbs energies we talk about in thermodynamics. Okay, but these atoms do not have atoms to bond, so they are at quite excited level. Okay, if there is any reason to change to some other state, they will be the first things undergoing the change, not the rest of the atoms. Okay, what happens when there is a force applied? When the force is applied, all other atoms remain in their positions. Only the atom which is here tries to undergo a change. Okay, what is that change? Is basically, you see this next atom, it has this blue color bond which is already there. What this atom does is it tries to bond with this atom below, which is below this white atom in principle, I mean in the beginning. So when these two atoms try to bond, what happens? This atom will be left out. So this entire line becomes the red color line now. Okay, so what has happened is this bond is broken and this bond is made. So this blue bond has moved one step to the left. So and then it proceeds further. The next, this green color is also, that is also going to undergo the same process. Okay, so that means these three red atoms feel like they are moving to the right. Basically, the entire plane of atoms are moving to the right. And we say this line, which is the bottommost line, that is called as dislocation line, and that line is moving. So this is the movement of dislocation. So in principle, it is basically breaking and making of bonds between the neighboring atoms. Okay, and the atoms are at excited state compared to the rest of the atoms, which are atoms of dislocation. Okay, so when I say defect, it's not a bad thing. Dislocations help in deformation. Once you give a force, they are the ones which are moving, not the entire crystal. If the entire crystal has to slide on top of the other part, it is very difficult. all those bonds, and look at this pink line here, that is going across many bonds. All those bonds should be broken and remade. That is very difficult. Compared to that, only in this particular line of atoms, bonds are broken and remade. If that happens with a very less stress, there will be movement of atoms. This is permanent movement. So in macroscopic scale, you will see that if multiple dislocations move like this, you will see a deformation happening. So this is the deformation mechanism. Okay. So whatever I told is written in words here. Okay. So this is the crux. Easier the dislocation motion, higher is the ductility. Means the ability to undergo shape change. Tougher the dislocation motion, strength is higher. Means you are reducing the ductility, means material is getting stronger. Okay. So that's the opposite effect. When we talk about strengthening mechanisms, there are multiple ways in which people try to strengthen a material, which is in principle reducing the ductility. So people try to do every shape changing with low ductile state, and then if they want to put it in the application, they want to make it stronger. For that reason, they will go for something called strengthening mechanisms. Okay, different ways are there to strengthen a material. All those strengthening mechanisms rely on this effect. Basically, they are trying to obstacle. They're trying to become an obstacle to dislocation motion. If that happens, the material gets stronger. Your yield strength and ultimate tensile strength will go up. Okay, so that is one way of understanding your strengthening mechanisms. Fine. Now we will connect these two ideas that we have just understood. Correlation between phases and strength versus ductility. So this is, I would say, rudimentary generalization, because this is not always true for some cases. I mean, there are exceptions to this, whatever I'm saying now, but roughly we can generalize. Intermetallic phases have high strength and hardness. Solid solutions have high ductility and toughness. Okay, so this is a very crude generalization. So how to achieve higher strength ductility combination? We want higher strength and higher ductility together. What to do? You may think that why don't we mix solid solution and intermetallic together so that we get good ductility and good strength. True, that is called as precipitation strengthening. It is one of the strengthening mechanisms which is quite frequently used. For example, nickel-based superalloys, they use one solid solution as matrix and one intermetallic phase as the precipitate. It gives a very good strength ductility combination. Okay, but this same property hunt is there in any alloy design. Even in for high entropy alloys, we will keep that in mind. What about this mechanism? Solid solutions with more elements give higher strength. We can think about this also, right? I said solid solutions will have high ductility and toughness, poor strength and hardness. How to increase the ductility and toughness of solid solution? Solid solutions are having some amount of strength because of solid solution strengthening. Basically, different elements coming into picture and they are blocking the dislocation motion to some extent, which is not very high effect. If we add more elements, then this blocking of dislocations can become more effective. Then more strength can be obtained for the solid solution. So that is one way of thinking about improving the strength of solid solution. Okay. So ductility is already there. How to increase the strength is the question. Add multiple elements so that you can increase the strength. So this is one idea. Okay. So this is the idea which was there in people's mind. Think about this one. This is one single element crystal structure. When we have multiple elements, this is how the lattice looks, highly distorted and all. So for a dislocation, those three red color atoms that I told in the previous slides, for that dislocation to move, it becomes difficult if the lattice is like this, with multiple atoms with a distorted lattice and all. Dislocation movement becomes difficult. So there are more obstacles to dislocation motion. Therefore, the strength increases. Okay, so this is how these things connect. So adding multiple elements to stabilize, I mean, to make one solid solution is one very good way of improving the properties. And the high entropy alloy philosophy of mixing multiple elements together in equal amounts, that also kind of matches with this target, right? So this is the first property wise direction that we get. Okay. So now we know we want to make multiple elements in one solid solution. Okay. So how to select the composition to achieve a solid solution like this? Which elements to choose? Is there any guideline? So that is the first question that we have. When more elements are added together, which will form easily? Solid solution or compound? So this is a tough question to answer. We can use phase diagrams. Okay, phase diagrams will tell us with respect to different composition and temperature, which will be the stable phase. Whatever phase diagrams that you have already seen basically are like maps. If you have a coordinate, you can tell where you are in a map. Similarly, if you have composition and temperature, you can tell which will be the stable phase. That's what a phase diagram gives you. Okay, for example, this one. This is an isomorphous phase diagram. I'm not putting any particular element here. Copper nickel system looks like this. Okay. So at high temperature, this temperature is in y-axis, composition is in x-axis. At high temperature, entire thing is liquid. At lower temperature, entire thing is alpha. Alpha is a solid solution. L liquid is a liquid solution. A and B are the two elements which are solute and solvent. They mix to form this liquid solution at high temperature. At low temperature, they form solid solution. Okay. And there are some in between temperatures where liquid and solid coexist. Okay. So this is a phase diagram where you have where you can take a combination of composition and temperature and see what phase is stable at that particular combination of composition and temperature. Okay. So can this give us idea about which 5 elements to put or which multiple elements to put so that we can form a solid solution? Multiple elements means not A and B. I'm talking about A, B, C, D, E. 5 elements. Where are the phase diagram for that? That is difficult. So this is one more thing which I wanted to put here to caution you. All phase diagrams are not as simple as this. There can be extremely complex phase diagrams like this. So this is a very hypothetical system where you have different horizontal lines and different things like eutectic, peritectide, monotectide. All those things are written. These are some specific reactions. Okay, so forget about this jargon. The takeaway point here is that all phase diagrams are not very simple. You have this sigma phase, delta phase, and all, which are basically intermetallic compounds. Okay, so there can be many intermetallic compounds. There need not be one single solid solution at low temperature. There can be multiple phases at low temperature. Okay, so this is how some real phase diagrams look. Although for one or two systems, you may have a phase diagram like this. Okay. Yeah. So this is the problem. Almost no phase diagrams are available for high entropy alloys. Okay, so which 5 elements to add to achieve which to achieve a solid solution is still a big problem now. So what to do? We can rely on something like this. Okay, so this is the phase diagram AB. Okay, this phase diagram can be experimentally made. People can actually take a mixture of A and B elements, go to very high temperature and see whether they are in one single liquid state. If yes, you mark that as liquid, and you can keep reducing the temperature and see where that liquid starts to become solid, and you can also mark a temperature where entire thing becomes solid, and below that it is going to be only solid. So like that, at different compositions, one can take different alloys and do this thermal analysis, heating and cooling, figure out these boundaries and make a phase diagram. So that is an experimental phase diagram. There are multiple techniques to arrive at experimental phase diagram. Characterization techniques like X-ray diffraction, all those things are used to make phase diagrams. Okay, so there are different ways. So that is experimental. What is the thermodynamic basis? What is the basis to understand this diagram? Why is this in this particular shape? Experimentally, yes, liquid is stable beyond this temperature, solid is stable below this temperature, all that is clear. But what is the reason? How to understand this scientifically? Which science can help us? That science is thermodynamics. Okay, so thermodynamics forms the basis for phase diagram, especially something called as GX diagram, Gibbs energy versus composition diagrams. Okay, what I've done is at different temperatures, I have drawn this Gibbs energy versus composition diagrams, and based on that, we can understand this phase diagram. Let me show you one by one. For one important reference I would like to give here, this is my YouTube channel, Thermomatter, it is called. The reason why I'm giving it here is I'm talking about something called Gibbs energy here. But the way in which your understanding of laws of thermodynamics from your mechanical engineering, they may not naturally evolve Gibbs energy unless you undergo something called as Legendre transformations and all from second law of thermodynamics. So how is that process done? What is the meaning of this Gibbs energy? Is it something like heat energy? Can we sense it? So these kind of things you will understand if you go through this YouTube channel. There are playlists available to understand these things. If you have genuine curiosity, you can go through that entire set of playlists. Okay. So this Gibbs energy, as of now, you take it as a property for a phase. Okay. What is phase? You have understood now. For each phase, there can be one Gibbs energy. Depending on the composition and temperature, it will change. Okay. So these Gibbs energies we can plot and they will form the basis for the phase diagram. Let me show you how. Look at this diagram. This is drawn at one temperature, T1. Okay, so you have one blue line, solid, and orange line, liquid. Okay. Okay. So this thing gives you where the solid is stable, where the liquid is stable, that kind of details. T1, T2, T3 are three different temperatures. You will see that liquid is the lowest in some case, solid is the lowest in some case. Whichever has the lowest Gibbs energy, that will be the stable phase. Okay. So therefore, you can mark it in the phase diagram and get the entire phase diagram depending on different temperatures. Okay. So this is how a phase diagrams comes from Gibbs energy. Okay. So now we have understood that there are almost no phase diagrams available for this thing. So we can look at the Gibbs energy of solid solution and try to minimize this. Therefore, intermetallic phase will not be stable. So how to minimize the Gibbs energy of solid is what we are going to see. Okay. So how to reduce the Gibbs energy of solid solution more. For that, we have to understand Gibbs energy better. Okay. So Gibbs energy for solid solution has this kind of expression. Gibbs energy for intermetallic phase has this kind of expression. Okay, so here this delta G mix ideal is there for solid solution, which is one extra term which is missing in the case of intermetallic phase. Okay, so what is this delta G mix? It is basically nothing but this delta G mix. I'm talking a little more. Okay, this delta G mix is nothing but something called as configurational entropy. Okay, so this configurational entropy we should try to increase. Therefore, we can decrease the Gibbs energy for solid solution. So here you can see T delta S mix ideal. So that is the configurational entropy of mixing. If that is increased, we can stabilize the solid solution. Okay. Yeah. So that's the idea of stabilizing a solid solution. It comes from this equation. I have one quote about this. We can skip it for now. So this equation is written in Boltzmann's tomb. Okay. So this also I would like to skip. I think we have only 10 minutes time. So this is an interesting video, tells about the direction of natural processes. So this is there in the YouTube channel. You can go and see. Okay. So this is the way to increase the configurational entropy. If we try to have more number of atoms, configurational entropy increases. That is why Gibbs energy of solid solution goes down. So this is how we design high entropy alloy. Okay. So this W is the one. S equals K ln W. This S is nothing but our configurational entropy of mixing. So that if we want to increase, we have to increase the W. Okay. So I guess my watch is showing some other time. I don't know. It's 3:20 now. Sorry, I'm a bit carried away thinking that it is at 3:30. I started skipping something. We have time, half an hour more at least. Okay, so this one particular thing I would like to say, because without the W, the proceeding slides will be little difficult to understand. So imagine this one. Let's imagine we have a box full of coins. All of them are showing heads up. Okay, let's say there are 1,000 coins. Okay, if all of them are showing heads up, how many ways in which we can have this configuration, that 1,000 heads staring at us when we open the box? There is only one way, because even if one coin flips to tail, we cannot see this 1,000 heads configuration. Okay, so if you see 1,000 heads, that is one configuration. If one coin is flipped, that configuration is disturbed. So how many ways of getting this is only one. So that is called as W here. You will understand this W little better if you go to this one. Let's say we shake the box a little bit with the 1,000 coins inside. 900 coins are showing tails, and 100 coins are showing, heads, and 100 coins are showing tails. This is one configuration, 900, 100. Okay. How many ways in which we can get this 900, 100? If we flip one tail to head, make it 99, and flip one head to tail, then we will again make it 100, isn't it? So that is one way of changing this state, but still the entire configuration is not changed. 900 heads and 100 tails still remains. I can do that for two coins also. Make two heads into tails, make two tails into heads. It is still 900, 100. Okay. So how many ways in which I can get this combinatorics I can use and figure out? It comes to something like 10 power 140, huge number. I shake the box further. I go to a configuration like this: 700 tails, 700 heads and 300 tails. Okay. So you will have 1,000 factorial, 700 factorial, 300 factorial. Do this combinatorics, you will get 10 power 264 ways. So this is not almost 2 times of this. This is 10 power 124 times higher than this. Okay, compared to the previous configuration. And now if we shake the box further, what will happen? We will go to eventually a state like this, almost equal amount of heads and tails. Okay, maybe little here and there, 520, 480, that's also fine. So what happens to this state, and what happens if we keep shaking? Okay, this is what we will get: 10 power 299 ways to arrive at 500 heads and 500 tails. Okay, so you get the point, I guess. If one tail becomes head, the other head becomes tails, it is still 500 heads, 500 tails. So in that way, we can have 10 power 299 ways in which we can get 500 heads and 500 tails. Only among these 1,000 atoms, 1,000 coins I'm talking about. But what is interesting here is, even if you keep shaking, can you ever imagine the opposite to happen? It is always in this way things are happening. When you start with 1,000 heads, you will eventually go into a state like this. Okay, it doesn't mean that there is some kind of a intention for the system to remain in this state and not go back to this original state. The system doesn't bother. The coins are simply randomly jumping. They don't know anything. Okay, but only problem is, even if they are shaking continuously, changing head to tails, tails to head, there is simply too many number of ways in which 500 heads and 500 tails can stay. Okay, so atoms jump, you see what is the configuration, it is again 500, 500. Atoms again jump, you are seeing what is there, it is again 500, 500. So there is no way to escape from this really high number of ways in which 500 heads and 500 tails can occur, because system doesn't escape from that. So this is a very subtle point which is observed by Boltzmann. He is very rigorously worked on this in statistical thermodynamics, and then he formulated this W and quantified into K natural log of W, and that is entropy. Whatever entropy that you have understood from your mechanical thermodynamics, the Q by T related kind of stuff, okay, the physical understanding of that was missing from classical thermodynamics. So when Boltzmann did his work on statistical thermodynamics, then things became clear that the entropy people study in engines is nothing but this kind of increase in number of microstates. So this W is called as microstates in statistical thermodynamics. Okay. So natural processes occur in this particular direction. Fine. So why are we understanding this now? We know that W, when it increases, that means entropy is increasing. Okay. So keep that in mind. So that is going to be useful to design high entropy alloys. So this natural process occur in the direction of maximizing W. Why natural process we are bothered about is whatever has higher W will be more stable in nature. It will not try to go back to any other state. Okay, so this state has the higher W. So this state will be more stable compared to the initial state. Okay. Yes. There is simply more number of ways to remain in 500 heads and 500 tails case. Again, this is one part of one bigger video which is there in that YouTube channel. You can go and have a look. And now this K natural log of W, we would like to increase the W. Which of the following two phases will have more W? Is it going to be this one or this one? Okay, so here you have more entities. So number of ways of arranging them is extremely high here. Here it is only one. Okay, so there is no escape from this. I mean, there is no W coming from this. Here you will have very high amount of W value. Okay, so having multiple elements in one single lattice increases the W, therefore it increases the S value. If entropy increases, Gibbs energy is going to go down because Gibbs energy is H minus Ts. That minus Ts term will be very highly negative, therefore the G will go down. If G goes down, solid solution will be more stable. Okay, so whichever has the lowest Gibbs energy is the most stable. So how to increase this delta S ideal mixing is by increasing the number of elements. Okay, increase the number of elements to increase the delta S. So keep the compositions EQ atomic. This is another information. Now look at this graph. It says if you have a two element system and you try to calculate the configurational entropy for that system, which is nothing but a formula which comes from K natural log of W, you will have this kind of shape. At the middle, it is maximum, like 500 heads, 500 tails case. At the middle, it will be maximum. Okay. And instead of only two elements, if we have three elements, 33, 33, 33% each, then what will happen? If we have four elements, 25, 25 each, then what will happen to this delta S configurational entropy? You see this one. This is how it goes up. Okay. When number of elements for equimolar alloys increase, mixing entropy goes up like this. Okay. So in equal amount, have multiple elements. So that is the hypothesis we are coming to finally. Look at this box. Increase the number of elements to increase the configurational entropy. Keep the compositions equiatomic. This is the way to maximize entropy and minimize Gibbs energy. Okay, this is the hypothesis we are coming to. So how you would have discovered high entropy alloys is through all this journey. Add multiple elements in concentrated amount or equal amount. Okay. Increase the configurational entropy of mixing of solid solution. Decrease the Gibbs energy of solid solution. Then stabilize the solid solution. Okay. Therefore, your strength ductility combination is better. So all this is fine. So this is the hypothesis. In all these cases, we are still talking about the science of thermodynamics and how can it be useful to stabilize a solid solution. Can it really get stabilized only by increasing the configurational entropy? That is another question. Okay. So this is our hypothesis. Let's see what has happened when this hypothesis was tested almost for last 2 decades. This one slide gives you whether the hypothesis is successful or not. Okay. So let's see this one. How many percentage of cases? This is basically coming from something around 640 microstructures, experimentally verified high entropy alloys. And this is their result. Percentage of systems which has one phase is about 33%. Systems which have two phase is almost 45, 46%. Okay. And there are systems with three phase, four phase, five phase, six phase also. So your idea of stabilizing one single solid solution over intermetallic phases has not worked out in all the cases. That is at least true from this diagram. Okay. There are multiple phases coming in depending on what alloy system we chose. Okay. Even in the single phase, we think that we are stabilizing a solid solution only, but there are cases where we get single phase intermetallic phases also. Okay. So that stabilizing single phase solid solution by increasing the configurational entropy is not working irrespective of which 5 elements, 6 elements we choose. Okay, it depends on what elements we choose. In the previous slide, I showed only number of elements. This slide here, I am showing only number of elements. I'm not telling which element. Here, I'm telling about equiatomic ratio of 2 elements. I'm not telling equiatomic ratio of which 2 elements. So depending on which element we choose, is it copper, nickel, cobalt, iron, manganese, depending on which element we choose, there are some differences coming. Okay, so therefore this hypothesis is not entirely successful, but we see that there is a role of entropy in these cases. At least in many cases we are getting single phase solid solution, and most of the cases we get either one phase or two phase. If you add these two up, you get about 70%, right? One phase and two phase cases. So there are so many cases which are having very less number of phases, at least we can say that. But there is something called Gibbs phase rule in metallurgy that says you can have multiple phases in equilibrium if you have multiple elements, multiple components in your system. Okay, at least that is not working here. So there is something that this configurational entropy does. At least it minimizes the number of phases. Okay, so that is one thing we can see, although our initial intention did not work out. Okay, so there were controversies popping up when people realize that this hypothesis is not working. Okay, so 5 to 35 atomic percent of more than 5 elements, and HES may also contain minor elements. This is how it was defined. And another definition was this configurational entropy value should be more than 1.5 R. This I told in the initial slides itself. Now look at this. If we have 5 elements, 2 elements 35, 35, third element 20, fourth and fifth element 5%. This is following this first rule, 5 to 35 atomic percent of 5 elements. But look at the configurational entropy value, it comes to 1.36 R. On the other hand, look at this alloy, 25, 25, 25, 25. Only 4 elements, and the configurational entropy is higher than this case. So can we have only 4 elements and still call it as high entropy alloy? Because this configurational entropy is higher than this case. So these two kind of definitions are not definitions, strict definitions. They're kind of broad guidelines only. Okay, so you don't need to take it very seriously, but you should try to stick to these things. Don't deviate too much away from this when you are designing a high entropy alloy. So people came up with other names: multi-principal element alloys, multi-principal component alloys, complex concentrated alloys, compositionally complex alloys, because we are not bothered about stabilizing single phase anymore. Okay, it can be very complex microstructure also, and it can be compositionally complex. You do need not have equiatomic. You can go deviate from equiatomic and form really complex compositions also. Also, baseless alloys means you don't have a base element here. Okay, so what people concluded is something like this, which I liked. There is no right or wrong answer, and the appropriate approach will depend on the intent of the work being performed. If you really try to have a precipitation strengthened alloy, let's say, you need not bother about having a single phase solid solution. You can make a precipitation strengthened alloy, I mean one intermetallic phase and one solid solution together, and you can still have your compositions following these kind of guidelines. What you will call that? You can call that as still high entropy alloys. Doesn't matter. The name doesn't matter. That's what the idea is. But still people use the word high entropy alloy. Although they don't get the single phase solid solution, they stick to the name high entropy alloys, which is used in almost more than 90% of literature. Okay. So the aim of the field has become broadened. People no longer bothered about making only single solid solutions. Okay, they just started exploring multi-components in the concentrated regime. So that is the target now. Whatever microstructure comes, that is okay. As long as properties are good, we are okay. We are not bothered about making only single solid solutions. Okay. To investigate the unexplored central region of multi-component alloy phase space. So this is the unexplored central region, means all elements in concentrated amount. That's the meaning. Okay. So this is the target of the, I mean, kind of a direction for the field right now. Based on this, if you see what are the different kind of alloys, high entropy alloys that are explored, people came with new names and new category of high entropy alloys. One is this one, high entropy super alloys, which has gamma solid solution matrix with gamma prime intermetallic precipitate, which is nothing but what happens in a conventional super alloy. There is one solid solution and one intermetallic, and the same idea is followed, but the guidelines for high entropy alloys are also included. More number of elements in almost equal amount, configurational entropy should be more than 1.6 1.5 r, all that is followed, but it is not superalloy, therefore it is called as high entropy superalloy. Okay. Then high entropy steels. When we say steel, it should be iron based. When we say high entropy alloy, it should not have any base element. But if you have iron as the abundant element, like 50% or so is iron, in the rest of the composition, more elements are coming, still in concentrated amount, above 5% and all. Then what do we call that? High entropy steel. That is a new category. Then eutectic high entropy alloys. Okay, eutectic is one of the reactions in the phase diagram, the complex phase diagram that I showed. In that, eutectic is one of the reaction. What it gives is two phases. In the two phases, there is particular way in which they arrange themselves. That arrangement gives very good properties. Both strength and ductility are very good for that kind of microstructure. So since that is result of something called as eutectic reaction, people try to see whether in high entropy alloys there are any eutectic reactions happening, and is there any microstructure that look like this kind of signature for eutectic reaction. And they did find, and then they called these alloys as eutectic high entropy alloys. Okay, again property wise that is very good. Then light high entropy alloys, which have low density. Okay, low density is always a hunt. As mechanical engineers, you know, if you want to increase the fuel efficiency of your vehicles, you have to reduce the density of your components. Okay, so light high entropy alloys are in that direction. Refractory high entropy alloys are for high temperature applications. Okay, the refractory elements like high melting elements, tungsten, molybdenum, vanadium, that kind of high melting elements are taken and they are mixed together to form high entropy alloys. So these are refractory high entropy alloys. Then immiscible high entropy alloys. This is a term which I proposed and I am working on. So here, this is again thermodynamics based phenomena where we do not get single solid solution. Inside the solid solution, we will get some clusters, or we will get two solid solutions which are forming due to some kind of a behavior of Gibbs energy. I'm not explaining that behavior right now. Okay, so that is a very interesting phenomena that happens in high entropy alloys. Okay, so these clusters are two phases which are forming due to this phenomena called phase separation. They give very high strength, something called as cluster strengthening and all. Okay, so in that way, this class of alloys also become important. These are immiscible high entropy alloys. Okay, so now you can imagine from the intention of making single phase solid solution, how diverted and expanded the field is. Okay, so these are the different class of high entropy alloys. Yeah, this is obvious. So now the question comes, how to select the high entropy alloy composition. Now that we know it is not going to form solid solution all the time, if we are intending to have certain microstructure, what is the rule, what is the source where we have to go and figure out this selection criteria? Okay, for that there are some simple methods. I already told phase diagrams are not available, so people resorted to some simple methods which are empirical rules and binary phase diagram inspections. Okay, so we'll talk about that empirical rule also. And there is a robust method which is called as CalFAD, calculation of phase diagrams. So this is a kind of weird acronym for that. So here Gibbs energy descriptions are used, means the different curves that I showed, Gibbs energy curves from which we can draw a phase diagram, I said. So that entire thing is basically the equation for those lines is Gibbs energy descriptions. People have figured out these Gibbs energy descriptions. That is the work of people working in this area, CalFAD. Okay, so they generate these Gibbs energy descriptions for various phases. From the competition among these Gibbs energy, you can get your phase diagram. Okay, so phase diagram is something that appeals to you, but how to get the phase diagram from theoretical means is what CalFAD researchers do. Okay. So here only binary and ternary, means 2 element and 3 element Gibbs energy data is made. The descriptions that I'm mentioning here, that is only for 2 element and 3 element system. But high entropy alloys are 5 elements or more. How do we get the Gibbs energy for that cases? Is basically by some geometrical extrapolation techniques from binary and ternary Gibbs energies. Okay, so it can be made. That's what I'm saying. When you have 5 or more elements, you don't need to bother about how to get the Gibbs energy for this. If you are able to get it for binary and ternary using various thermal analysis and even physics based techniques like first principle calculations and all, they all give Gibbs energy. Okay, so there is a procedure called statistical fitting. Using that we can get the Gibbs energy. Any question? Gurudi Venkateshwar Rao. Is there any question?
Mute yourself, please mute yourself.
If you can mute, you can try, Dr. Padmanabhan.
I am muting, but
Okay.
I am not getting.
Okay, fine. Okay. Okay. So the problem here is whether we have all the binary and ternary Gibbs energies assessed already. If they are present, then we can make a database, and using that database, we can calculate a phase diagram, even for 5 element system. But what if those are not available? So that is the challenge in this area, and it is the databases are being continuously improved. So we will talk about simple method, one simple method, this one. So this is a delta parameter which takes into account composition, which is C, and atomic radius R. Okay, this R bar is average atomic radius of all the 5 elements or 6 elements that we are adding. So if this atomic size difference, this kind of it kind of measures what is the difference between atomic sizes of different elements. If the atom sizes are almost same, then it is easy to form a solid solution. That is the idea. So this person, Hume Rothery, they empirically figured out that if atoms have close atomic radii, they can form a single solid solution. Okay, so that is done for binary ternary solid solutions. That's what empirically Hume Rothery were able to observe. But here, this is done for a 5 component system also. So it's a kind of a broad guideline again. It is not a very strict parameter. Even if it is obeyed, we still see cases where single solid solution is not followed. Okay, people say this, if this delta value is less than 2.77, solid solution will form. Somebody else says it need not be 2.77, it can be 6.4. Okay, so how much is the difference between atomic sizes of these? For that, there is no strict guideline, and this also is not obeyed in all the cases. So you can sense the rudimentary nature of these parameters. So exceptions are significant. These are not decisive, but kind of indicative. On the other hand, Gibbs energy is proven to control high entropy microstructures. Okay, so people have done extensive CalFAD kind of studies and showed that Gibbs energy is enough. Why to go for all these things? That kind of conclusion. But still, not everyone can have access to these Gibbs energies, and periodic table is enough to get this atomic radii data and all. So with that, people are able to do some calculation and get some indicative idea about solid solution will form or not. So these simple rules are still quite widely used. And these simple rules do not rely on Gibbs energy. So these are various papers. Fine. Another method is phase diagram inspection. So I will tell it very briefly. If you have a 5 element system or 4 element system, let's say this 4 element system, 4C2, that is the number of binary combinations you can get from this. Okay, from a 4 element system, you can get 6 binaries. What these binary phase diagrams say, because binary phase diagrams are available. If you take something like ASM Metals Handbook, volume 3, you will find phase diagrams for all the binaries. Okay, so these binaries, what do they say? Do they show one single solid solution for a big range? If yes, let's take only those binaries and mix those elements together. Therefore, in high entropy alloy also, we'll get that same single phase. Okay. So this is one kind of simple method, which again has its own drawbacks. Okay. I'm not talking about the drawbacks now. The robust method is CalFED, which is my research area. It's the direct method for phase diagrams making. So conditions we have to give, like composition, temperature, pressure, things like that. Then we can do something called Gibbs energy minimization. Whichever phase or combination of phases have the lowest Gibbs energy, those will be the stable phases. So there is no question of increasing the configurational entropy and stabilizing only solid solutions, because even intermetallic phases can have certain increase in configurational entropy. So it's not a simple thing. Gibbs energy is the only parameter we should rely on, which takes into account enthalpy also, not only configuration entropy. So this is the entire procedure of what happens in CalFED. So I will skip it for now. Some results I will show you, because this is important. When we talk about phase diagrams, for two element, there is one A, one B, copper, nickel. You can make a phase diagram and tell where which phase is stable. When we have 5 elements, how to visualize the phase diagram? So this is one way here. This is called as phase fraction plot. Here, with respect to temperature, volume fraction of phases is plotted, which means in one composition, 5 elements, single composition. If you change the temperature, different phases will come into equilibrium. I mean, different phases will be stable phases in the microstructure. And what are those phases? That this label tells you the name of the phases, crystal structure also. And what is their amount? That can also be directly read from this y-axis. Okay. So that is that is one representation. This is called as phase fraction plot. And in the right, you see something called as isoplectal section, which has some restrictions in the composition in the x-axis. This looks like a normal phase diagram, composition versus temperature. But when the composition, chromium is, let's say, it's changed here, COFeNi, 3 elements are there. Now 33, 33, 33 in the left extreme. As chromium increases, these 3 will reduce equally. For example, if chromium reaches 10, in the remaining 90, 30, 30, 30 will be occupied by COFeNi. Okay. So this is one way of visualizing a 5 component space. But still, these are slivers of 5-dimensional phase diagram, 2-dimensional slivers into that. None of this will give you a good picture of the entire 5-dimensional space when you have 5 different elements. Of course, there is extra dimension. Temperature is also there. 6 dimensions are there. So this is the way that high entropy alloy community uses. Okay. So yeah, this is about Gibbs energy composition plots of binaries, chromium, nickel, cobalt, chromium. For them, we can only plot Gibbs energy composition plots. And from that itself, we can get some insights about which phase will be stable in the microstructure or not. Okay. So this is one paper of mine where the method is explained in detail. So I'm just saying, from the plots itself, without going for a phase diagram, you can get some idea about what your high entropy alloy microstructure will be. But the plots are only for binaries. So this is a very interesting thing. If you have only binary Gibbs energy data, that is good enough. You don't need to use a CalFAD software like thermocalc and all and bother. Only get these Gibbs energy descriptions, use your Excel or something. Then you can figure out these diagrams and different quantities that are mentioned here, like D and all. Then you can say how easy or difficult it is to stabilize one phase in your microstructure. Fine. These are a little more applications. I think I will stop. 10 minutes are there. I will leave it for questions. Okay. So the promising properties I will show and finish. Okay. So this is one paper which puts high entropy alloys here in the graph. Fracture toughness is in y-axis, yield strength is in x-axis. Very high fracture toughness is found for certain high entropy alloys. It's basically cobalt, chromium, iron, manganese, nickel, that high entropy alloy. And people have figured out that has extremely high fracture toughness. Tensile strength levels of above 1 gigapascal, 60 to 70% ductility, which is extremely high. Exceptional fracture toughness, 200 MPa meter power half. Okay. So this is like a diamond in the rubble. You can find n number of high entropy alloys mixing any 5 elements from periodic table. But some of them are like diamonds. They give you extremely high properties. Look at this one. Okay. Here, compressive yield strength versus temperature is drawn. Inconel which is the famous nickel-based superalloy, is here, the red line. MARM 247. Okay, that is another superalloy. Haynes 230 is another superalloy. These superalloys are here, and these lines with these kind of circles and these yellow symbols, these are for certain high entropy alloys. You can see which is the high entropy alloy here. Okay, they have much higher properties compared to superalloys, and even the temperature capability. In x-axis you have temperature. At extremely high temperatures, higher strength than nickel-based superalloys. So this is extremely interesting. And when we say higher strength, can we really use that without considering the other things? For example, how about the density? If density is extremely high and temperature capability is also high, can we really use that alloy? No, there are restrictions coming from weight perspective. So we should not have high density. So people actually find out this compressive strength divided by density, that parameter, and draw this. Even in that, high entropy alloys are found to be much superior than nickel based superalloys. Okay, so this is promising. Okay, so like this, there is a huge hope in the field, and as I told, there are millions of alloys to be explored. So those of you who are interested to delve into this, there is at least 2 decades of literature available, and few books are available. At least 150 review papers are available, so you can start with that. So I will finish with this quote from Carl Sagan: somewhere something incredible is waiting to be known. So this he said for finding out intelligent life somewhere in the galaxy. Okay, so I think this is suitable for high entropy alloys also. Thank you.
Thank you, sir.
Thank you. Any questions?
Thank you for such a clear lecture, sir. It was very clear and we could understand a lot. Dear participant, anyone, any questions?
I hope this is appealing to mechanical engineers. This was not too much into materials, I guess.
But the way you explained was very, very clear, sir. We could able to catch up all the basics.
Thank you. Thank you.
It was really very clear and very smooth, and I really liked your way of presenting the lectures.
Thank you.
Dear participants, any questions?
Hello.
Yes.
Hello.
Yeah, Venkateshwar Rao.
Hello.
Yeah, I'm able to hear you. Please tell.
Sir, we can hear you, sir.
Yes, sir. Yes, sir. Yes. Madam, this is Empirical from VVIT. Sir, we are showing the dislocation chart, sir.
Yes.
In the third one, I think you say that the perfect crystal. So in that I found that there is 3 rows, 3 atoms which are separated in that place.
Yes.
Hello, sir, madam.
Voice is not clear. It's breaking. Is it so, Dr. Padmanatha, for you also?
Yes, sir.
Voice is breaking.
Sir, Venkateshwar, sir, can you repeat, sir?
The dislocation chart.
Yes.
Like edge dislocation. Sir, showing one dislocation chart, madam.
Yes.
Yes.
I think I am audible, madam.
Sir, one thing you can do, sir, can you type your question in chat box, sir? Otherwise, your voice is breaking, sir, in between.
Hello.
Now you are clear.
Yeah.
You can.
Yeah,
ask,
yeah.
Okay, 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 madam. Yeah, yes, sir. We are showing one edge dislocation chart, sir.
Yes.
In that, I think that there is the last chart. It will show that 3 rows or 4 rows are there is completely filled. Outer side with 3 atoms which are red mark.
Yes.
Yes, sir. Can I know what is the difference between there is unfilled or it is a perfect?
That is not a chart, first of all. That is a crystalline structure. where you have certain atoms which are continuously bonded with neighboring atoms. There are these three red atoms. Below the bottommost red atom, there are no atoms to bond. Okay, so this kind of things are called defects in the crystal. So that is called as edge dislocation. You already said that word, edge dislocation. So this defect comes due to many reasons. Okay, we will not go into the reasons now. When it is present inside and you apply stress, this dislocation is the first one to move. The reason is because it doesn't have atom to bond below. Therefore, it is at a excited state. If you give any stimuli, that will respond first. Stress is a stimuli. So therefore, this dislocation responds first and moves to the neighboring site. Is it your question? Am I answering to your question?
Okay, sir. Okay.
Okay.
Okay, thank you, sir.
Okay, thank you.
Any more questions?
But one question has come in the chat box.
But bond breaking and making involves a lot of energy.
Way more than plastic deformation. Actually, it is plastic deformation that we are talking about. Bond breaking and making involves a lot of energy, that is clear. But what if we want to move one part of crystal over the other part of crystal without these dislocations? In that case, we have to break all the bonds between two planes of atoms and move the entire crystal one atomic distance, let's say. To do this, it requires extremely high amount of energy, as you rightly said. But if that is the amount of energy required, no material can be deformed. But in practice, we see a lot of metal forming processes, rolling, forging, so and so on. Okay. So how these processes are happening is because of the help from these dislocations inside the crystal. These dislocations are just one line of defected atoms. Okay. When the stress, the original stress that you require to actually move one crystal over the other crystal, even if you give 1/10 of that stress or 1/20th of that stress, depending on the material, you will see that this line of defected atoms respond to that stress. They move immediately. Okay, so that is a permanent movement of atoms. Like this, if there are multiple dislocations, usually 10 power 2, 10 power 3, 10 power 8, that many number of dislocations per centimeter square will be there inside a material. So that picture of atoms sitting nicely in a crystal structure is not the reality. You will have lines of dislocations like a web, like the spider web inside the house. Like that, you will have a web of these dislocations all through the material. When you apply stress, they move. Okay, not the entire crystal. So that is why you have a lesser amount of energy. Yeah, thank you. Okay.
Any more questions? You can also share your feedback. Any questions you want to ask, you can ask, sir. You can unmute yourself and you can ask. Or you can type in chat box also. Actually, most of our lecturers, assistant professor from private colleges, sir. So this is the time where they will return to homes through buses.
Okay.
So they may be busy in that.
Okay, no problem. Yeah, 4 o'clock, not already.
They will be returning now back to their homes. Okay. Sir, thank you, sir. Thank you for
madam.
a very clear lecture, sir. It was very, very useful and very clearly explained. You have explained it very clearly. If possible, share the PPT, sir. We'll share it in our.
Sure, I'll do that.
Thank you, sir. Thank you so much.
Thank you.
dear participants, we'll meet tomorrow at 10 a.m. as usual. See, according to ACT, actually we have to take the feedback also. So if someone can respond, it would have been good. Okay, no problem. We'll meet tomorrow. Madam Saraswati, madam. Madam. Okay, I'm ending the meeting. I will also post the attendance link in WhatsApp group also. You please submit. Thank you, everyone. Tomorrow we'll meet at 10 a.m.